in our head, and then one neuron can get connected to 10,000 other neurons. So almost 10 to the power 15 number of branches which exist, and having a very efficient communication among that. So there has to be some kind of scale-free network where the total average length of communication from any node to any node will remain constant even if you go on increasing the number of nodes. That kind of setup and communication links are established in our brain. So it is one of the finest existing, very high connectivity network. This is number one. Number two, if you see the human body, the total number of sensors it has. So simply on our skin, there are billions of sensors. And there are many more other sensors, different types of sensors. Now, if there is a mosquito bite in your leg, without seeing where it has bitten, you can, with your hand, you can just strike it there. So see the localization algorithm. Out of so many number of neurons, without any address, please be very specific about this, I am very specific about this. No neurons have addresses. Neither sensors have addresses. Without having any address, it can perfectly localize that where the mosquito is biting. So you have a sensor network on your body, and then see the amount of computation. We have massive parallel computation, and to have synchronization, there should be serial communication. So brain is a massively parallel, synchronized, serial machine. So it has a large amount of computation. What else you require in 6G? Sensor network, you talk about IoT, then communication, you talk about brain communication, and then computation, massive AI, that is again in brain, massive computation. This whole thing gives rise to a model which is not yet perfected, has not been realized into real life. So therefore, what we have done is that we have started studying about the brain, taking the models from the brain and trying to see if that is applicable on our machines or what we can do on our machines. With that, if you see this, these are the parameters. I may be wrong somewhere, but see, people are talking about 6G, and therefore I thought that it is better to talk about the 6G also. Now it is where, so when you see the parameters, something from 4G has come to 5G, extension of those parameters in some sense, and then from 5G to 6G, again there are the one, but this extension is very high. So you go from 10 Gbps or 20 Gbps to 1 terabyte, 1 Kbps. Similarly, this goes to terahertz range, and so on and so forth. Mind it, when you go from micron level to nanoscale, whole physical properties changes. So all nanotechnology has to use a different kind of phenomena rather than simply extending the micro to nano. Because we are talking about at the atomic level. Talking about the atomic level and trying to see the forces there is not a simply summation of all the atomic forces. So different phenomena arise in nanotechnology, and therefore most of the quantum computing things will start talking about the nanotechnology, not on this. I fear that when you go to 6G, will these micro things will be usable or not at that level? So therefore this extension from 5G to 6G in terms of parameters may not be valid in my view. But anyway, we can extend our imagination and talk about that. Then, but the real world is, there's another problem with when you talk about the extension of technology. We exist in a real world. When you talk of 5G and 6G, think about the world today, and any kind of criteria when you transfer technology from one thing to the other thing cannot take place in a digital manner. You cannot have a country where everyone is 5G and suddenly they will come to 6G and some people will have 4G, 3G, 2G, etc., etc. There will be some different kinds of speeds and all of them coexist in a real world. Any management or any extension in terms of future has to also think about how to correlate it with the lower technologies at the same time. So if you do not create a business model onto that, things will not be completely successful. Although technology level you can talk about the 5G, 6G, etc., etc., but the same technology should not be totally separate from the earlier ones. So there should be a seamless transfer, I will talk about. So seamless transfer must be there from the lower technology to the higher technology, and that is one of the requirements which all industry has to also consider. So therefore we live in a real world. There is another aspect of that, I will talk about that after some time. So now there is a heterogeneous world, and therefore the specifications are heterogeneous. Most of the distributions, even if you talk to statistical distributions, they at once come to a homogeneous thing. Why? If you talk about heterogeneous things, then you have to apply different constraints at different places, and trying to create one parameter for the distribution will be very, very difficult. So therefore, any assumption in terms of homogeneous things and therefore idealizing the parameters will not be correct. We have a heterogeneous world. Why I am saying heterogeneous world will make a difference, let us see like this. Now when we talk about communicating from one place to another one, we think that it is independent of the content. So the view of communication is that there are 2 points, there are 2 nodes, connect one to the another, and the data is either audio or video or EEG or whatever. It can be transferred through that device from one end to the other end. This is a view of communication. So therefore we forget about the data format, we forget about what is the data generating process. Because after all, data is not important, data generating process is important. Please mind that. If I give you 3 numbers, 2, 3, 4, you cannot make out of it. 2, 3, 4 will get meaning or information only when we attach that what process has created this 2, 3, 4 and what they really indicate. So you cannot separate this data generating process with the data and then send it to some other place and then again try to redefine the things in your own way. It is something like take a glass and break it into millions of pieces and then try to find out what was the shape of the glass. Okay? So they try to combine them in different manners and then therefore find out the shape of the glass. But if we know a priori that it was a glass which has been broken and therefore we have to compute a glass which has a shape like this, it will be very easy to make that shape. So information is not only data, information remains in the structure of data, the relationship between the data. And the relationship you have to find out. Number 1. Number 2, information is meaningful or not. We always try to forget about the meaningfulness of information. So in 3 data, 2, 3, 4, you can assume that this is a arithmetic progression data. You can assume that you take the average of 2, 3, 4 and say that 3 is the cost of some pen. Or do anything, any kind of model with the 2, 3, 4 you can create. But if I say 2, 3, 4 represents a zombie, now you will say what you are talking about. So when you associate this information with a real world thing and this linking or mapping is perfect, then you say that this information is meaningful. So the same thing we do in our brain. A brain creates an inner side world of the outer world. But whatever we create, I am speaking here, if that has no meaning, you will not listen to me. Why you do that? Because what I am speaking has something in parallel in the real world. It is explaining some real phenomena in your brain. And therefore my information becomes information for you. This connection, if you forget, and try to create in imaginary way anything from the data, it will not be correct. So this is another very important problem of the real life data. While we are talking about the communication in our class, and through psychology, I found that most of the communication is visual. All of you are seeing my face. Why you are seeing my face? You can only hear my words, and therefore can understand. But no, more than half of the information is going from my face to your head. And that visual communication, or non-verbal communication as we call it, has more meaning, has more direction, as you know in what context I am speaking. So that is also very, very important, and therefore the form of the data, so it is audio or video or EEG or what, and it is taken in what situation that data has been measured, is very, very important to understand and find out the new information out of it. So all these things leads to cognitive computing, and therefore we have created a cognitive computing systems. Now let us talk about this system and environment, local versus global, because that will lead to the new kind of model which we are talking about, which we call as the federated learning or meta-learning, whatever the word you want to do about. When you analyze a system, so you say that this is a system and this is the environment. So at once you separate the environment from the system. And then many times, especially in computing, you forget about the environment. You think that because we have created a system synthetically for our convenience, so that system is what is we have to analyze. So all information resides within the system. Why do you think that this assumption is true? If you have not carefully separated the system from the environment so that minimal interaction is there, and assuming that this interaction will not affect the system, we can analyze the system in itself. In communication you talk about channel, but then the whole environment is only in the form of channel characteristics. So the whole other than system is represented by channel characteristics. But channel characteristics are different in different environment. So if there is rain, the channel characteristics will change. If there are some occlusions, then the system characteristics will change, and so on and so forth. And the whole world is related in that sense. So when that is related, you have to see that really a system is complete in its sense or not. This is one part. The second part of it is, which we call as the local versus global, and this becomes one of the very important part in all machine learning system. So we talk about system versus environment, local versus global, and then the problem is local, which we are trying to understand as a system, but even the local things have different levels, number one, and number two, the information is global, or the knowledge is global. And that is which we call as the coherency. So if I create a new information, one piece of information, and someone else has created another piece of information. Now these two informations may be contradictory. So which one to be taken? And what is the basis of which one to be taken? So what we do is that we try to combine these two information, and if they are contradictory, then we have to find out what is the reason for contradiction, and at that point we will say, okay, these are connected, but if the situation is like this, then this statement is true. If the statement is this condition is different, then this statement is true. So therefore, connection has to be established between these two information, and in that sense, the whole world knowledge is coherent. Any world knowledge which is not coherent with the world knowledge will not be considered as a true knowledge. So this coherency check, how do we do that? We write a paper, you write a paper, other people write a paper, publish it, let others read it, they will do some experiments onto it, and if both the papers are coherent, it will be considered as correct. If some paper is there which is not coherent, it will be considered as wrong. So this coherency check is very, very important. In that sense, the whole knowledge is global in some sense. And therefore, when you analyze the structure of the data, which has information, and when we talk about the structure, it is only not becomes spatial. The time structure, time hierarchy, which is the the seriousness, serial things. A happens after B. So this serialness has also a structure, time structure. So how it is the temporal structure and spatial structure of the data will give you the relationship and therefore the information out of it. So machine learning has to analyze this structure, temporal as well as spatial. Both the structures are important. And then structures when you talk about, so if I say want to know the average temperature of this room, where should I measure? No, one can measure it here and say that this is the temperature of this room. Someone can measure it there, or someone can measure in front of my mouth and say the temperature is higher. Okay? So, the temperature of the room has to be average of all the data. Now, because there is a structure of space which is inside this wall, if this wall would have been a bit farther, then that average has to be more farther. So the size and things of the wall is telling us how much how many number of measurements has to be taken and in what way it can vary, etc., etc. So this can be called as the immediate context. But then there is wind outside. The temperature of the room is also dependent on the wind outside, and if the window is open, then that temperature will vary. So you have the next context level. Similarly, you can have more and more context levels of. So immediate context, next level context, and so on and so forth. At some point you have to stop and say that, okay, I assume that this much is fairer for this kind of experiments. So that gives you the practicality of the level determination and how much data and how many things should be analyzed. So, and that is being done by human beings. All these things I am talking based on the human being analysis. So local from global. There is one more very important thing which is very, very important. The method of human being is not bottom up. So I do not collect large amount of data, and then based on that data only we will come up with a new information. So if you start combining data from the bottom, go on combining at the higher and higher level, if you assume that at the top level we have a global information, this is wrong. Because the brain works in a different manner. What brain does is that it creates an hypothesis and it gives a proposal. So if I want to solve a problem, you will ask me that, okay, these are the problems, but what do you want to do? I say that analyze the data, you will find out what do you do, what you want to do. You will say, no, that is not what you expect, what experiment you will do, and therefore what you will expect, and therefore if that expectation is correct, then fine. If not, then you redesign your experiment. Okay? So you have to always come up with a prior proposal, a prior hypothesis, and then hypothesis can be tested or not tested. So, this prior hypothesis where from the machine will get is one of the challenge of. That can a machine get a prior proposal, can get an hypothesis on its own, or the human being will assume that there is a hypothesis and then machine will only be used for testing that. Assuming that this is a problem at present is a challenge, a big challenge, then when you say that our hypothesis is correct, the proposal is correct, now there is no one measurement of correct, there is no absolute truth like that. Okay? So only one way of doing the things correct is not a method. So why do you think that there will be only one solution to a problem? Anyone? Why not many solutions to the same problem? Yes, there are. And therefore, in brain, it goes for population code. Multiple solutions. A, fine. If A does not work, B, fine. C, etc., etc. And there is a population of spiking neurons which participate into the process such that, even if one of the neurons is absent or degenerates or dies or does something, some link fails, even then the solution will be there. So much so that different parts of the brain have been found out participating in the same process, and also in different processes the same part does something else. So multiple things are related in one information, and one thing or more, some things can give more than one kind of information. So this is many-to-many mapping. There is no one-to-many or many-to-one only mapping. It is many-to-many mapping, and therefore any process of degeneration will not affect the total process of taking decisions in our brain. Even if problem is not solvable, it will come up with some idea saying that, okay, it may work. So this is one of the very important part of human brain. So we have to talk about such kind of effective, and instead of talking of the correct solution, we will talk about effective solution. And effectiveness depends on what do you want to do. So therefore, while choosing the parameters, so in the morning we were talking about the security. Now, if you see the things with the help of security, then you will find out that mixing the information does not happen. We want to keep it separate. And therefore, trying to secure the machine learning processes will be very, very difficult. You have to share the data also. So people are coming up with, it is good that, anonymized data. So even big data, all the text data is being shared with all the people in the world, so that everyone can develop it and then try something else. So that's why the machine learning viewpoint and this viewpoint of privacy are not sometimes or many times matching. Similarly, you can have another point of view. Say, for example, if I say that we cannot give up 4G today, and therefore we should develop a system which is both 4G and 5G. Now you have to make different kinds of mix and match. So what is good, what is effective? If you say that only if the error defined in this manner should come less than this, then only it is good, otherwise it is not. But this is a choice. Choice based on cost, how much affordability, access, and so on and so forth. Different types of technologies which has come up, and so on. So therefore, let us talk about the effective solution, rather than talking of correct solution only. Correct is in one point of view, other point of view can have different correctness. And this decimal numbers and these numbers have created a big confusion. So if someone asks you how many percentage of marks you have got, if someone starts talking about 98.12347893345 and go on speaking for 2 days, you will say stop it. Okay? Because that much correctness is not required. And there are many assumptions which we have already put into the model where the total error, maximum error possible is more than that. So just computing to a high precision does not make it the things more precise. There are many sources of imprecision. So that is what is important. So therefore, good versus effective, high performance versus better infrastructure utilization. These can be at least two opposing requirements. Whatever infrastructure we have, we should utilize it in a most satisfactory way, most efficient way. Or seeing a single transmission of data, one stream of data, and saying that here the speed should be more than this. Both can be requirement in different situations, and therefore machine learning should be different for these two. What I am saying is not one is not required or the other is not required, but machine learning cannot be a general model that this is the only correct model. Well, so therefore different point of view, and different point of view has to be incorporated into machine learning. Well, other than that, a good algorithm, effective algorithm will not come up. So now let us come to the problem of our this, if I talk it as MIMO, so multi-user MIMO. We are talking about at least at two levels, so you can do one at the RF level and other at the baseband level. So at the baseband level, if one MIMO structure can go up to, let us say, 8 port or 8 MIMO structure, can we increase with that 8? Yes, we can. Given the situation, we can increase that with the 8 if we model each user. So user modeling becomes very, very important, and that is where AI will work. AI will help you better. What is the user modeling? User spends the whole day in a particular manner. See how they move. So each user, if you think that at 9 o'clock someone will be there in the MIPT. So you will assume that at 9 o'clock if you make a phone, it will assume that it will be in MIPT. So if you know about your friend, you know where he will be there if you know his daily routine. The same thing can be done by the machine. If the machine knows the mobility pattern of that person, then that infrastructure of which he or she is a part of can do something for that. Instead of someone has living at some place and every time it is assuming that that person is there in that range. So mobility pattern is one of the problems of all this one. This is just one example of having the user modeling. The user modeling can be the type of user. You know, some people require high technology things, very high stream connections. Some people require not so high stream connections, only for talking, only for something. So similar user habits and things can be there, which can include environment in which the person is there, mobility as I have talked about, and many more things. At present I will not go into this. In the morning people have talked about this. So user modeling is what we can do better in this case. However, this user modeling we will do in the same case as, what is the problem? If I want to know the user, the mobility of all the people in this hall, can I have one model? Well, it's confusing. But the other extreme can be that let us have a user model for everybody, each one, individual. Although each individual can change their mobility, someday I want to come to Russia, so that day my user mobility model which has been created in the India will not be correct. So therefore, separating that, you should have some systems where if it goes beyond the user model things, parameters, then it has to take care by some other service methods. So that way, if we use that, what we can do is that we can at least categorize them into two levels. So there can be two groups in this hall where one user model, one kind of mobility will be done by one group and the other kind of mobility can be other group. The question can be at one extreme it can be all, at the other extreme it can be only one. We have to choose at different levels. So any model which is created with less number of things combined together, less variance I will say, then that model will be better suited to all the people in the group. So how many number of models should we create? So that is what is called as federated learning, that create some clusters. Clusters should not be chosen randomly. Please be very clear. Clusters should have some numbers and should have some property common. So if we are taking a mobility model, then if all of the people are working at one point, then it can be called as during the office hours, all the people can have one model. This is the kind of criteria I am trying to define. Similarly, you can have different kinds of criteria. Based on that, you do the clustering of the users. And then that cluster should be used, have one model. And in this manner, one can create local models, but this is not only ultimate thing. All these local models has to be combined to also a bit global model. Why? This is another trick into this. One is that if I created a local model, a new person joins. What will you do? Or a new group comes. So what do you do? If you want to create the total model from the data, so when to create the data? This is another problem in machine learning. I will come to that a bit afterwards. But, we require data for creating a model, and model will be used for people. So initial data, where from it will come? So that's what we do is that if there is a global model, you can think about that nearby groups, whatever is there, that global model can go back to the lower levels and can create a hypothetical model for that new group, which is an imagined proposal. Now, that model will get data from each individuals in that group and will tune this into one. So federated learning has to be done at both ways. Bottom to top, creating local models, from local models to the next level global model, next level global models, and for new groups and other things it comes back, because if you want some universal kind of design, then you have to use the global level at that level. And then when you come back at the lower level, then it has to be coming from that more tuning from the next level to the next level and coming at the end where you can have the exact parameters tuned with the help of the data you obtain from this. So this kind of learning has to be done at different levels, and this cannot be done simply by this one. Let me go fast. How much time is there? 5 minutes. Okay. So let me go this. So these are the different kinds of models, statistical models people have these days working on. This is also one of the papers in IEEE, not mine, by others. And it talks about fuzzy modeling and statistical modeling, both together. What we intend to do is that fuzzy model can give you a better proposal-based models. So therefore what we are working on is what we call as a type 2 fuzzy level, type 2 machine learning models. And the type 2 is, so we talk about fuzzy rule induction. First you have to do clustering. So you can have clustering where you can have a regression term, and this can be type 2, where what we talk about type 2 is something like this. So type 2 fuzzy model is that in fuzzy set you have a membership function. So all the elements are not equally member of the set. So different members are different membership values. So some member are more members than the other members. So we assign a value between 0 and 1. So some element x is member 0.5. Some other element x, y, can be a member 0.6. So you assign a value between 0 and 1 as a membership value of that set. And we work on that. Now, instead of having a crisp membership value saying that it is 0.6, this itself can be fuzzy number. So when the membership value is again fuzzy, this is called type 2. And you can go on like this. So membership value is fuzzy, then that membership value is again fuzzy, and at that membership can also be fuzzy, and in that way you can go to type n level. Why this is the method? As I told you that there is a structure at the lower level, then in the next level there is another structure. So this is a type 2. If you want to go at the higher level, it can be type n. So in probability case, one of the problems is in statistics, general probabilistic statistics, the problem is that it is a closed world assumption. All the possible events must be known a priori, which is one of the difficult tasks. What happens actually is the set is not completely defined. So we do not know the universal set. Rather we create the universal set kind of thing from the samples itself. When you collect data and try to create the world, it is not that the world is there and you try to create the samples. The problem is inverse. From the samples you have to create the world. And you don't have the idea about what is the complete world. In such a situation, using probability distribution is one of the difficult tasks. So what we do is we use possibilistic distribution, which in the fuzzy sets. The possibility distribution can have some subjective factors. I can say that 0.3 part I don't know. Okay? And based on that we can do all the analysis. It has problems because of that, so it is not totally normalized. And therefore all the distribution will not never add to 1. It may not add to 1. When you apply some of the algorithms like intersection and union, etc., the whole membership distribution added together can become more than 1, so you have to re-normalize. But I can create my own distribution function, possibility distribution function, based on the information I have from the context or from the global model. So fuzzy logic has the advantage better than the probability distribution in the sense that subjectively I can assign models, which can be, after getting more and more data, which can be refined more and more. So therefore, our view is that if we create a fuzzy logic type 2 and do the fuzzy learning like we do for all the other machine learning cases, it is possible to learn the user behavior where the user should not be represented by one number, should have a vector at least, and that vector will be based on different kinds of parameters or features, what we call as this one. And the learning can be done like in deep neural network, like in machines, and therefore we can apply all these operations of deep learning network, which we have applied in many other cases. One more thing I will, So these are the things which we can talk about. There are many kinds of neural network framework, deep neural network framework, which is already available. One can use this, but we are working on fuzzy levels, so that training and this or the rule are based on fuzzy type, not directly some number taking from this one. So the connection values we can put on as fuzzy rule based values. That is where it differs from. So this becomes a fuzzy deep neural network. This type of work has been done in many other domains, and I think that it is very good, it is possible to do here in this case. So at the end, learning requires time and resources. See here, we wanted to preserve time and resources. For that we wanted to use AI. But for using AI we require more data and time and all that. So there is always a balance. Of course, deep learning, if it is done a priori, then at the dynamic time you will not require that time. So assuming that you have resources and time earlier, while it is executing before that, so you do all this work before that. However, there is no guarantee that this will correctly define the new situation. So you have to, like in time series prediction, you have to always go on predicting the things. And one of the problems of this kind of deep neural network is that it is only considering the things in parallel. Mind it, especially the language part, language has a serial structure. So if you change the order of words, the meaning of the sentence changes. So analyzing the words in parallel of a sentence is very, very difficult. And same is true for many of the concepts. Therefore, the new technology talks about LSTM, long short-term memory. In deep learning, this LSTM has become now the buzzword. Now you have a stack of LSTM, one-way LSTM, bidirectional LSTM, and many more. Many kind of such techniques have already been refined and has come to on stage. But mix of this convolutional neural network, LSTM, and many more other kinds of reinforcement learning, etc., etc. Some people have worked on the Bayesian network, where the prior has been created as the meta prior. So you have a prior and you have a meta prior. Mind it, the conditional probability part is a kind of tuning with a particular specific user. The prior part is a model. Now, if you have many such distributions, you can create a meta prior of the priors. So even at the probability level, one can go at different higher levels. And some people have tried to work onto that, and some people have reported good results onto that. So these are the various kinds of methods of AI which can be used in all the problems. I will just request all of you to please consider that if you use the deep learning as a black box, it is not going to succeed. The deep learning thinks if you create a model yourself and then let the network learn, then you know what the network is doing. So therefore you have to take this approach. Please see that everything cannot be done in parallel, because the data, knowledge, information has some hierarchy, some kind of relationship with each other. So only non-dependency things can be in parallel. So one must analyze the dependency. And this dependency is there in the knowledge itself, which may not be visible from the data only. So therefore, taking all these considerations and then doing optimization for various types of parameters depending on your requirement will give you better and effective results. With that, I will stop. I will invite more discussions. If you have questions, please.
So, any questions? If no questions, I have one. So, Professor Hillary, how do you think what is an area
Получилось на мою флешку, да?
which would have
Получилось, да?
if we apply AI,
Как?
what is like the highest impact?
Не, я хотел от вас ее получить.
Yeah. So as far as I know, as I told you, that user modeling will be my main place. Of course, we talked about cognitive networks if you want. So frequency, you talk about in the cognitive radio, if you remember the people here, which are related to the telecommunication. So cognitive radio, people talked about, so you have two types of users, primary users and secondary users. And then they have these different kinds of needs. So what they said is that instead of fixing the frequency or the radio part for each individual user, whenever they require, you give it. So resource management has been done based on that time requirement. This kind of things have developed. There are many papers on the cognitive radio, but I assume that has not succeeded well. So the technology has not gone far beyond. So there are some basic requirements. I don't think AI will help much. However, some of the user level things where you share your resources, that is a fundamental thing, based on the different requirements. Sometimes I am talking, so you do not require a very high kind of bandwidth and data for that. And sometimes I am doing some other work. So this resource sharing based on AI, creating a prior model. Because at that moment, if you start talking about who needs what, then there will be totally mismanagement. So prior modeling is very, very important, and that can only be done through machine learning. This prior modeling. So in my view, multi-user things, sharing of the resources is the place where AI should be used. I'm sorry, I'm not very specific.
Okay, thank you. So any other questions? So then let's thank Professor Kiwai for this lecture. So let me invite our next speaker, Professor En&T-2019 from Indian Institute of Information Technology.
Thank you, Professor. So, good afternoon to all. Before beginning with, actually, I would like to clarify two things. First one is being a roundtable session. This is something I am just throwing some thought, and we can then discuss. We want, I would like that some input should come from your side actually. This is more important. This is the integral part of the roundtable discussion. It's a roundtable discussion. Okay. So, what you will find in my talk, I am going to talk on very, very fundamental issues of information theory, and which was suggested by the Shinner. And what can be done is a way ahead, which is not there actually. We have seen several generations of the cellular communication system. A lot has been changed, but what has not been changed till date? This is something which I am going to discuss, and I would like that we should start thinking over it, and let us see that if something can be done about this. So I'm saying that we are supposed to explore the applications of artificial intelligence. This is also my perception. I have a hope that yes, AI can help in this particular regard, and this will bring some benefits. And just for yeah. Okay. So just making a ground, preparing the ground for the discussions, I am just trying to introduce a few very, very fundamental issues. And this is something about the Shinner. As on date, if we try to see, then definitely we can see that our communication system design can be precisely divided into three parts. And there is a Shannon era, and then there is a pre-Shannon era, and then just now something has been started. and definitely after the tea there is a session of a discussion. I'm going to elaborate on this particular point, what is the post-Shannon era, how we are moving, and what are the indications which are there. But as of now, if we try to figure out that when actually people started thinking that something beyond the base landline telephone communication system, something is there, it is not performing around 1920 or so, and you all know actually all this history. I am just making the ground as I said. So around 1920 or so, actually we know that people started thinking over it, that what is the reason that communication system, when I am putting more load, more connections on a line, performance is degrading. And they did not have any answer, but definitely they laid down another channel, and the problem is solved. And then it is the Shannon only actually he defined the channel capacity, and then people find an answer to it. But still then people used to laugh, and they used to say it is a theoretical concept, very good theory, but no practical use. And only after after a long time, when the Shannon's work was introduced, it took a long time when actually its concept has been implemented. So what precisely has been changed if we try to figure it out? Then before the Shannon, precisely the communication systems were designed giving emphasis on the messages. We want to faithfully transfer the messages. And Shannon innovatively argued that it is not the messages, but we should consider the information content of the message, and then accordingly we should design the system. And in the by this, two developments took place. Okay. And the first development is source coding. It is suggested that okay, there is redundancy. Whenever we are communicating some messages which are generated by some user, they are carrying the information, and inherently it is there that this messages has some redundancy, and that's why another way of saying this thing is the information is not maximum. So Shannon said, okay, there should be source coding scheme, and precisely what we are doing in the source coding scheme, we are trying to remove the redundancy. Okay? So from where these redundancies are coming into messages, precisely these are generated by the source. Okay? So source has generated some messages which were having the redundancy, and the first outcome of the Shannon theory, and they said, okay, this redundancy should be removed, and definitely all the communication systems we know they are having the source coders, and it is an integral part of any communication system, modern communication system that we are thinking of. So if we further move ahead in the communication chain, then we also find that the redundancies that we have removed at the source coding level, then we are creating the redundancies our own, isn't it? All the error control coding techniques which we have been using in the 2G system, 3G, 4G, 5G, still just think of it, what we are doing. We are just trying to see that less number of redundant bits should deliver the maximum bit error rate, but yes, it is there. Okay. So somehow we are generating the redundancies ourselves. System is generating the redundancies, and these redundancies are precisely have some objective, some goal, and we know that how it started from the convolution code of the 2G, and now we are reaching to the turbo codes and beyond in the 4G and 5G systems. But actually the philosophy has not been changed. Only thing is somehow we are doing some improvement, we are getting some gains, and accordingly there is a error control coding technique which is being used, and definitely this trend may further go on, and there are certain codes which shows that actually the Shannon limit has been reached, or it is actually they have achieved very, very close to the Shannon limit. And then this is another fact that random appearance is better. All this theory is something that we know. So what point I want to make? I want to make a point what in the morning session someone said, the professor from Germany, and he said that it is the nature which is evolving itself, and whenever it is evolving itself, then definitely we should take note of it. Okay. And I want to give you 2-3 examples to this which are there. So the first one is we all are working in the communication field, and we know that multipath propagation. How we started, we said in the second generation system it is an enemy to us, and we try to see that we should counter it and we should avoid the multipath propagation ill effect. And when we reach the fifth generation system, actually we are saying, okay, we want to use the MIMO system, and then the interference is good. And someone has presented in the morning session that other good effects of the interferences. So this is something what has been changed. Okay. My point is, first of all, this that if we try to see that the importance of the interference has already been there for the acoustic communication, isn't it? Several years back, actually, people have already established this particular thing that how our perception or our decision is becoming better when we try to concentrate on some audio signals. And that is, suppose we are in a crowded place, and definitely there are several sounds which are coming over there, and we can concentrate, and we can ensure that whatever sound that we want to hear, we are able to hear it, isn't it? So people said that how it is becoming possible. Then one of the theories simply says this thing, that there are several more multipath components which are being simultaneously processed by our brain, and then because of this, this is becoming possible. Okay, so my point is that it was there, and it was known several years before, and nowadays when we are trying to evolve the wireless communication systems, then precisely we are getting the same result once again, and we are saying, okay, multipath is good. Okay, and another different field is there, and that different field is something which is belonging to genomes and genes and the bioinformatics, biotechnology people. And let me briefly tell you that genes consist of two parts. One is the exon part, another is the intron part. And in the protein synthesis, actually, it is known. All this is known that only exon part took place, and introns are eliminated. Okay? So for a long time, actually, the people of the bioinformatics and the biotechnology have been discussing on this particular part. If it is not useful, then why it is there? And recently, actually, some results are coming up. People are coming up with the findings that actually the intron is also playing very, very important role in the entire process. Although it has been eliminated in the protein synthesis process, but people have defined that what are the purposes over there. Okay. And the third one is also general observation. Actually, the newspaper news I have seen here and there. And it was earlier, whenever someone is having any surgery for the stomach, people used to cut the appendix. And nowadays, actually, people are denying. And it is a finding. Actually, it is a redundant thing. But actually, now it has been found that okay, this is something which stores good bacteria, and it should be there. It is not redundant. Okay. So my point is this, that there are redundancies, and even in fact in the last lecture Professor U.S. Tiwari was also saying about these redundancies. So there are redundancies here and there, and these redundancies are there for a purpose. Okay. So the point is this. Okay. If somehow I can analyze these redundancies which are generated by the source, which actually I am removing at the source encoding level, because Shannon suggested this thing. Okay, Shannon suggested this thing, so we are doing it, and we are seeing that okay, there are some benefits. Okay, and then we are adding the redundancies at the error encoding level. So the point is simple: this that the redundancies which were generated by the source, why can't we use these redundancies for the error correction purpose? Okay. Or can we have some mechanism? But and we know that what mechanism we can think of as on that, the best thing which is available for this kind of purposes is the artificial intelligence or the machine learning technique. Can I have a model? Can I try and attempt some different modeling techniques, different artificial intelligence techniques? Can I develop certain models and can I test that, okay, this redundancy which I am removing from one end, actually this is something which is useful for the error correcting purposes. And my friends, I tried something. Unfortunately, there is no result, and that's why I'm thinking here only. Just giving you an idea for the discussion. And yes, I would like to know your opinions. This is all from my side on this particular topic. Thank you so much for the question.
So, any questions on or opinions? How to use AI to increase redundancy, useful redundancy?
Can you say some words concerning using some ideas for using AI in combining of source code and channel code?
Yes, right.
What, as far as I know, as far as I understand, we need first of all understand what physical basic is for using AI, and then try to implement this tool.
Right.
And at current time, I think there is no quite understanding what physical principles we need to use
Precisely.
to combine it.
Yes, right. So actually, that's why there is the problem, na. We do not know actually what we want to achieve. How can we achieve this? What kind of model that we can build? And as I said, actually, we tried in 2-3 different ways. We have a group and people are good at MI and this thing. But our model did not give any result actually as far as the error control coding capability is concerned. So actually that knowledge is something which is the thread is something which is missing. So somehow actually in the roundtable discussions when this point is discussed, then probably people may start thinking and sometime actually may come up with this idea. This is the basic issue.
If you already performed some experiments, you see 2 or 3 attempts to apply AI to this type of problems. Can you share more details about it, because it's very valuable for others, maybe not to repeat your attempps and to search in other places?
Oh, certainly, no, not an issue. I'll certainly share.
So can you now give a few more details about what you have tried, some ideas what you have tried to apply, and why do you think they are not working? Maybe if you have an idea about why they are not working.
Yeah. Actually, what we have done, actually, we tried SVM. We took the initial samples of the users, and then we tried to train it different kernels. We tried to train, and we have seen, okay, its generation accuracy has been increased, but actually when we introduce the noise and the interference patterns into it, then those gains actually disappears. So these are the different standard models. Actually, we tried neural network. Some models we have done, you know that how it works. So some models actually we developed. We tried to implement with the original signal, where high sampled signal, more or less it becomes very similar to the analog one, such a high frequency signal, so that most of the information should remain there. But yes, the results are not as good. Not good actually, not as good. Actually, they are the results are not showing the error correcting capabilities because of this artificial intelligence, whatever model that has been created. So this is the problem.
Thank you. So, any other questions? Or maybe somebody can share their own experience in applying some techniques from machine learning to his research. Okay, so let's think ours. So the next speaker is Irina Vasieva from Huawei Technologies.
Thank you for the introduction. Is this microphone? It's working.
It should work.
Okay. Maybe. So I would like to speak about some problems we encounter in our work and what kinds of neural networks we try to apply successfully or not, and why we think that reinforcement learning ultimately may be the best answer to our problems. And this title allows me to structure my talk easily. So first I will tell you about some problems. For example, as you know, there is a base station and it transmits data to mobile users, and we want to keep them happy, basically for everybody to speak successfully, to download video successfully, to have a good bit rate, and so on. So the data undergoes many transformations on the way. There is some, for example, voice which gets transformed into digital signal, and then a few times back and forth. So ultimately we do transmit it by air, by analog signal as well, and during all these transformations it can be distorted, something may be lost, and basically we want to optimize ultimate experience on the user side. So, for example, on the left you can see what is the novel feature of 5G, that we concentrate beams from base station individually on each user. So we can pre-code signals individually, and we want, ideally, probably in some situations, to have all these beams orthogonal. So this is one of the problems, and also we want to say one of the problems which I will be talking now also concerns how better to pack information into the signal. So we want to use our channel as effectively as possible. And this is one kind of problems, how to effectively use our resources. And another part of problems is how to fairly split the resources between users. Suppose if we are in different groups and we only say these guys watching videos, these are voicing, and this browsing web, and everybody has different indicators of quality. For example, somebody needs a very small delay, especially important for new 5G technologies. We want low latency for certain operations, and for video streaming we probably need more uniform streaming, so there is no gaps, no stallings. So it also makes our indicators to be specific for a specific kind of service, specific quality indicators. So basically we are dealing with optimization under certain constraints. For example, there are power constraints of on each cell or on each piece of the cell, and this is like a brief overview of types of problems we're dealing with. And this is one particular one where we try to pack as much data as possible into one transfer block to transform. We can pack a lot of information, but it will have high probability of being lost on the way. And if we pack too small, then we don't use the resources as effectively as we could. So loop link adaptation. It goes step up, and if transmission is successful, and step down if it's not. And you can see here that you can see that there is some room for the gain. So we want to use these green bars and not follow red steps up and down. So the initial suggestion was to use AI to predict true channel state and pack information more effectively. But channel state may change rapidly. This is one of the problems. For example, we know about state from our measurements, and you can see that it is very spread in time. So we have a reference signal which is sent in one moment of time, then measurement happens at another moment, and then we receive our record in the next moment, and then there is still some gap before we actually transmit something. So to predict this channel quality is also a problem in itself. And if it just oscillates more or less randomly, then it is similar like working on the trade market. It is basically nothing that you can do, but we cannot say we are not playing. It's not our option not to play. We have to transmit something. So we have to have an opinion about what is the channel state. So this is current algorithm which has a target of error rate. Basically, if 10% of everything gets lost, it's okay. And it works surprisingly well, but we want to use AI to do better. And this is just simple densely connected neural network which takes in all the measurement information as features and then does simple classification, solves classification problem and outputs whether we will receive acknowledgement or not, whether this piece of data will be successfully demodulated. And then we take a maximum of this curve here, we take the peak, where we think that probability of being successful is counterbalanced by how much data did we actually take. And it also works more or less okay, but what is bad here is that, for example, here you can see that we have some gains for mobile users who move and channel changes. But we want an adaptive solution because these reference signals are user specific, so we want probably to have solution for each user individually. We don't know the method users mobile manufacturer implanted to calculate this information that we have. And we also want to take into account different indicators of user quality. So ideally, we would like to have a joint solution where everything is taken into account. The methods of users and users' traffic and to keep like everybody happy. And what is bad here that it is hard to train on all particular situations. We want our neural network to provide a good answer in all kind of environment. And to beat this, probably we want to also move back to online adaptation, and not only use some pre-trained model, but use some model which will be trained and process new information. So this is where we think reinforcement learning can be helpful, and we basically want to use this method of trying, failing, and trying again, and failing again, and ultimately learning what to do, what is the right thing to do in every particular situation. And this method, what is its difference from a normal adaptation algorithm? Because it can also be so complicated. It can have parts of a basic neural network. For example, this part of densely connected neural network. Another thing it can use full channel matrix information, which can have huge dimension. It can have, it is not just one channel state, it is like huge matrix, and have many resource elements which are used for transmission, and to average it, some complicated formulas can be used, and often, as we engineers know, more complicated doesn't mean better performance. It may mean more accurate in some sense, but not necessarily better performance. And this is a problem which also can be outsourced to neural network. Say, this is your huge matrix, use convolutional neural network to output one number, which is channel state, or 5 numbers, or whatever, to compress this information somehow. And because we want compression, we want this to work within half a millisecond. So on this particular slide, I wrote some formulas corresponding to reinforcement learning, but as you probably know, reinforcement learning mainly makes use of delayed value. So it is not that on every time step we receive some reward. For example, was our attempt of transmission successful or not? We also want to be successful in the long term. For example, if we did transmit a lot of information to video user, but it had stalls on the way, he still will be not happy. So this is, in the end, it will be still bad result. So reinforcement learning takes into account the situation that in the end, what may happen that the user will be not happy, and this negative value will be back propagated to our current decisions. So maybe it's better to keep low quality but be more stable. So this is why we want reinforcement learning. And another interesting thing, which part of reinforcement learning, is the ability of using competitive neural network as a critic network. And of course we can use, for example, now our densely connected neural network as a critic because it has decent performance in certain cases. But more interestingly, we can use our baseline algorithms as critic. We can say, okay, we have now currently used adaptation algorithm, and let's split them. Let one work this time moment, another this time moment, another this time moment, and compare. Because we have so much information to transmit, basically, so it is to our benefit that in many cases we have a long time to allow ourselves to average over. So this is very convenient, and this allows us to use various kinds of critique in reinforcement learning structure. And this is good, and this is, I think, important for, at least for some cases, in some problems that we face. So this is about it. So I wanted to say that in our programs of radio resource management, we want to transmit radio resources and provide users with as much data as possible, and also with other possible indicators of performance to improve everything. And we want to say that for data which is changing, for example, not changing in time, but changing in between users, we want to use some adaptation algorithm, because it is hard. Maybe, of course, it's possible for reinforcement learning to change everything and say, this is your particular matrix of weights, then fix it and you go and use it. It may be possible very well, but of course there are different complications, like how often to retrain, how often to translate this knowledge to other sites, to other locations where to use it. And this is why we think that reinforcement learning is the way to go, and it has better formulations because we have direct keywords, whether user had or not, whether information was transmitted or not. It doesn't require us to have labels for training. So this is about it. Thank you for attention.
Thank you, Irina, for your talk. Any questions?
So, one clarification I wanted, that you said that expectation value has been substituted by some Monte Carlo simulation.
Say it again.
In this is Monte Carlo estimate. Last line. No, the same signal. Slide here, so. Next.
Not previous, but next.
This last.
The last sentence.
Yeah. Expectation is replaced with the Monte Carlo estimate. So this is the estimated value. And you are trying to find out the error with respect to this.
Yes.
Because there is absence of real data.
No. But in real, are you asking why we use Monte Carlo simulation? Because we are working on a simulation platform. And this is the reason, so we can allow ourselves to do so.
Okay.
If you say that it's not allowed in real life,
Okay. Other methods of reinforcement learning you tried. I mean, this is a kind of Q learning, I hope.
yes, this is good to learn, but this slide is for a particular problem. It is for.
So other forms like temporal distance 0, 1, 2, K, TDK, Albert.
Yes, and this we actually tried for improving video performance.
Yeah. Thank you.
Now I have you called Back to the Future topic, part of your topic, online adaptation, Back to the Future.
Yes.
Why? It's not so complex, but very efficient.
Yes, because it is well known, and it is what is currently used, what's been used for decades, right? So, but now when people
Currently used, but not back to the future.
I mean, that in the future we can as well use old adaptation techniques plus to machine learning, not to replace machine learning, replace adaptation. Because if it's often what they do on machine learning, they collect all the data, they train, and this is one answer you get. one fixed matrix of weights, but without adaptation, it actually faces a lot of complications. And this is why I probably want some combination of this. So it's not just only reinforcement learning as such, it is more like online adaptive reinforcement learning. What I think must work, not just some particular algorithm of machine learning, but something which will be able to be trained online.
Any other questions?
Could you provide some examples which properties of the system you were changing during the optimization process?
During what?
During optimization process.
If you say, if you allow me to speak about this particular example of packing transfer block sizes, then we could change channel state, we can change speed of users, we can change like interference pattern and so on. And in this particular situation, you see this is only one fixed speed, and this results for the neural network trained for this particular speed. User go in all possible directions for not line of sight channel transmissions, or all paths are possible to reach for the signal to reach one user. If you have in mind some particular features, I can answer.
No, I was just wondering about concrete examples. Thank you.
Any other questions? So, what is for you like the most impressive example of application of machine learning in your field of application or study?
You know, unfortunately, in my experience, it is like research. I sit in the office, so all I see it is basically examples which are not in the product. So for me, I believe it is still to come some impressive example for it to be actually implemented and working in, I mean, for actual mobile phones. So all examples that I'm familiar with, it is not maybe proven useful so far, especially reinforcement learning. It is like a hot topic, everybody is doing it, but to even to name a single example when it was truly fast all the way, it's hard.
Okay, thank you. So, Alexander Victorovich, can you give us guidance what we should do next?
Thank you. I think that we can have a short break, coffee break, and then return to discussion, round discussion on all topics that was already said, and any other topics concerning using AI in telecommunications. I think I can say some words in this discussion after break. Thank you.
еще там 2 осталось?
Ладно, сейчас.
Слышишь? Напиши Яков. Типа, где это будет. Это так. Надо специалиста. Надо фотос.
Это. Зачем?
Потому что камера не просадочится.
Всех в смысле? Прям всех, как я могу мотать и все. Проблема.
Нет.
Так один же будет говорить.
Да, понимаю. Вот последнее не видно. Так ты поставь ближе ко мне пусть будет. Все равно такой тебе. Они кстати, может покушать там ничего не делаем. Пойдем там спросим про прослугу.
Подожди, сейчас пойдем про прослугу
Да
посмотрим.
нет, ты знаешь, какого прослугу? Че, погоди, я хотел.
Все хорошо.
У нас... Они будут тут сидеть? У нас просто закрываются мониторы.
А я не знаю. Что сказали? Сказали, что будут здесь?
Так, ну, интервью, да.
Угу, хорошо.
Так.
Так, да?
Что, давай что-нибудь придумаем. Можно, слышишь? У нас 10 минут есть, да?
Угу.
Есть классная идея, но она такая себе. Можно тот стол поставить сюда. Видишь, вот тот прибить.
И что?
Поставить на него камеру. Или вообще на этот стол поставить.
Чего? Как камера?
Ну, типа вот, насколько она
Блин,
длинная?
никак это будет выглядеть, как ты сказал.
На том столе камера стоит, все.
Зачем?
Так.
Сюда вот, ну, в смысле. Опа, нет, тогда там не будет. А если вот здесь? Тогда здесь очень далеко. Блин, я вообще стол туда перенес просто. Это самолет.
Ну, это такое себе.
аккуратно взять и по чуть-чуть переносить с глубокого.
Тебе насколько перенести надо?
Минус вот сюда.
Ну, а в розетку все розетки. За 5 минут оставшихся.
Какие 5?
15 сюда заходить.
Ну а что делать? А что делать? Ну, давай попробуем.
Никто не заметит.
На стол попроще поставить.
Так.
На стол камеру.
А.
И там это держи. Вот это допустим.
А его опустить же можно сейчас? Эти треногу. Давай опустим эту треножку. Как ее опустить?
Нет, это не так.
Вот так. Как
Опускается на вот эти.
И как? А, типа растянуть их просто? Так это что же, наверное, вверх-вниз лезет? Ну, давай. Меня видно. Даже так. Ну давай сяду. Будешь смотреть.
Что так криво-то?
Ну давай листай.
Нет, это ты так ее выровнял.
Это не я.
Ты что?
Ну, да разберемся потом. Ты посмотри, как видно. Листай. Ты понял, поворачивай.
Нет, не понял.
Ну сейчас выровняю, гляну. Это самая меньшая из проблем. Смотри сюда вот. Не, опускается на вниз. Ну давай, смотри на меня.
Всех видно.
Так на меня посмотри. Так как их видно в каком масштабе?
А это не видно.
Ну так
Все
вот,
хорошо.
вот на меня посмотри.
Ну, хорошо. Только надо...
Ты зафиксируй вертикально, чтобы она не ездила. Норм?
Да. Да. Надо чуть правее.
Типа ты слишком не приближай. Смотри, кстати, проведи, как когда заряжается. Это меня напрягает. Сейчас чувствуешь?
Да, это пробой. Нет.
Что это?
Пробой.
Ну да. Тебе кофе взять?
Это как вот ты нажал? Блин.
Ну, обосрались. Ну, обосрались. Ой, обосрались. Можешь отцепить на секунду. А, хотя не, лучше не стоит, да? Ну, давай.
А это так и должно быть? Или нет?
Нет.
Так, я он так замотал. Не надо.
Возможно. Вот это через низ. А.
Нет, подожди, вот это так было. И это именно так. Я не могу.
Ладно. Да ладно, пофиг, какая разница.
Ладно, ну вот так вот будем водить.
Ну, типа,
на постоянно.
всех видно? Да, я буду водить, ты будешь слушать. Или ты будешь водить, а я буду техать.
Кто-то будет водить. Нет, придется все-таки вверх-вниз.
Нет, ты вверх-вниз зафиксируй.
Зашли, ну, здесь должно быть так, а здесь не видно.
Да ну лучше тебя вверх-вниз, лучше не
Ладно.
дергай.
Нет,
Возись вверх-вниз. Как?
вот она здесь.
А.
Вот это.
Понял.
Вот. Никого не знаю. Так, елки.
Да блин, лучше мою камеру взяли, она, по-моему, лучше снимает.
Да. Не успел.
Давай историю в Инстаграм подписчикам запишем. Блин, а на самом деле, вот ты жалеешь, что согласился? Ну, ты, понятно, не жалеешь. Я жалею, что согласился. Но минус английский, минус физра и минус маклов. И минус ОКТЧ контрольная, которой я готов.
Yes.
To let my bosses know, so they asked me, "Are you able to talk?" I said, "Oh yeah, probably I can talk."
No. At least for me, I was very bad the front, so that I don't miss.
They are not present, so they don't witness my shame. You see.
On the round table, and I would like to give word to Professor Shivari to start our discussion.
So, discussion means discussion, which means that is only some people should not speak. So, questions which are given in that, I think it was published somewhere.
Yeah, you can take these.
Yeah. So, there are 3-4 questions, but it is not necessary that only around that we should discuss. We can take more questions, and we want that everyone should speak as much as possible. Try to discuss on few topics. It is basically about AI learning, and therefore the questions are basically based on that in reinforcement signal. When you do reinforcement learning, what you do is that there is a reinforcement signal. So it is not a supervised learning. It is not an unsupervised learning. Reinforcement learning is known to be in between supervised and unsupervised. So instead of having a teacher signal, you have a signal which is called as a critic signal. And the critic gives you reward or punishment. One of the problems in reinforcement learning is, how do you know that solution has been obtained? Because there is no clear-cut convergence. And without convergence, if your reward is changing every time, so when did you stop? When you will stop and say that our circuit has learned. This is one of the basic problems of reinforcement learning. So people come up with some idea like, you can have a semi-periodic solution. So if the solutions are state 1, 2, 3, then 1, 2, 3, 1, 2, 3, if these states are repeating, then you assume that now it has attained a convergence. Because the same sequence of states are being this one. And this may not be totally periodic. It can be 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and then again 1, 2, 3, 1, 2, 3, 4. So several kinds of periodic sequencing or semi-periodic sequencing has been obtained, and then people have come up with convergence. So criteria for convergence in reinforcement learning is one of the toughest question, I will say, which is there, which if everyone can think about, is one very important problem. The second problem with all such kind of learning is that getting the real data. Simulated data, people have worked on simulated data and come up with solution. But the simulation equation itself has an inbuilt regularity. And any real data will be irregular. So when you train your system on the regularity created things, it will learn the regular structure. It will not be able to know about the irregular part. So getting real data collected from the real experiment in systems which are working with the users is one of the great problems. And if some companies have data, they do not share with the research people. This becomes a big problem. So how to solve that? If there are some industry people, I will say they should come up with some kind of resource, store services to the institutes and researchers and all over the world. So some kind of data sharing should be there into that. Otherwise, data is becoming a big problem in this one. The third question, which will be related to the problem is that even if you converge, so there are two things. The information has two aspects. One we call as a similarity, and other is we call as a dissimilarity. People think that dissimilarity is irregular thing or noise or undesired or so on and so forth. This is not so. Especially if you take the medical data. So a doctor looks for irregular data. If I take the data of breathing, and a lot of work has been done onto this chaos modeling on breathing. So they have create a model which can create a chaos model and generate the data for breathing. In that case, the regular breathing pattern is learned. If doctor sees everything regular, then where is the disease? So disease is an irregular pattern. And therefore, knowing the regularity is not a problem, knowing the irregularity is the problem. And therefore, in such cases, removing noise is very dangerous. So therefore, both aspects has to be considered. Similarity is that thing which makes it a member of a set, a property which is regular, and dissimilarity is a property which makes the thing unique. Information has both values. One is regularity, other is irregularity, uniqueness, making it different from the others. That's why it has a name. Any name must have some difference from the others. Otherwise, it is the same thing which is the others. So this commonality and difference. Based on that, you have one kind of machine learning network which is called as the GAN, Generative Adversarial Network. In the GAN, you have a regular part and you have another part which is dissimilar part or variability. So regularity you can compress, variability you cannot. So that's why how to measure this, and if you use the same metrics for both, measuring similarity and making it that 1 minus similarity is dissimilarity, that becomes totally wrong. Then the uniqueness part you will never be able to capture. So that's why in many of the information retrieval systems, we have both factors combined together, similarity as well as dissimilarity. So how to create a matrix for these similarity and dissimilarity, I think is another very big challenge to all machine learning algorithms. So one should also think about that. This, in my view, are the very important questions, and I will invite that if you have any idea or if you have any experience, or even if you want to ask questions, then that should be there. Before that, if you want, I can tell the others to speak. Anybody has questions or want to add to this?
I would comment.
You have a comment.
Yes, about data, about how it's our difficult life that we cannot get real data. But especially for reinforcement learning, I think that the main problem, not the main, but additional problem is even when we do have data, we don't have feedback to our algorithm. So if we act on the environment in some particular way, and either we doing simulations, basically learn how a simulator program works, and probably we know this in advance. Or for real data, we want to feedback to all possible algorithms we want, and this is, of course, more complicates things. So, and I also wanted to comment on this first point that you mentioned, that how do we stop, how we know that we converge, that in my specific job we have certain very simple problems, and in them we don't probably even care about conversions. We can say, okay, this is better than baseline, and we can compare on with baseline in real life, in real time, so it becomes less of a problem. And thanks.
I want to say some words now about another issue in utilization of artificial intelligence in telecommunications. of all, we can look at classical system for digital transmission of information. In such scheme, we have source coding, channel coding, channel itself, modulation, channel itself, the modulation, decoding, error correction decoding, source decoding. And in this classic scheme, I can say that I see some fruitful places for using of artificial intelligence, rather clear places for using in source coding. Then I say some words about it. Not quite clear how to use efficiently artificial intelligence in channel coding. And moreover in modulation. For me it's a big question. Then channel estimation, yes, it's the field for artificial intelligence use. And of course, in this question, your Professor Tiberi issue is very useful if we can distinguish noise part and another part, regular part. It's also useful, for example, in source coding. Of course, if you have some experience in this field, that people who have some experience in this field understand that, for example, a video with low noises is compressed more efficient than noisy. If we can, and this is also field for artificial intelligence, intelligent distinguishing extruding noise from another information. And into this scheme now we need for telecommunications add, I think, one more part, behavior of user and prediction of user behavior. Maybe with using of artificial intelligence can be very fruitful part of the system, as already this issue already was said today. This is one part of my speech. I think it is very important task to define the most important parts of the system to implement artificial intelligence, machine learning, and so on. And before I say another part of my speech, maybe somebody can tell something about this issue. Wants to tell.
Hello, dear folks.
I have some question.
Please come here so that
Oh,
the question is to everybody.
Yes, I have some question, or we can describe it as some problem. How we can control reinforcement learning? Do we have some way to control our narrow algorithm? Let's discover such a situation. We have a laboratory stand. For example, this is data transmitting in IP network. We have some complicated, some big, some good system where we modulate some IP protocols, modulate a graph of transmitting data. So okay, we learn our system to, for example, in case of resource management, and after that we work in real system, and we have our reinforcement learning. And after collecting new data, real data, we have some new amount of weights. So we have some new situation. Our algorithm can work in different quality. When we have a real system, we have no ability. We can't we cannot have some mistakes, because if we have mistakes in the real system, we can drop all system. So can we create, for example, some hard algorithms, simple algorithms that can I don't know, correct that can correct our narrow algorithm to provide good quality in all ways of working. Maybe it can be. Maybe we have to create some systems with hard and soft solutions to control our real world. That's it.
I think that in this case, maybe a solution would be possible by combining your, if you have already some methods to control your network parameters, but you want to improve on them, so you can combine them with, so you have your already established algorithm, and you know how to measure quality of the work in your life situation. So you should set a threshold and say that if quality in my system is higher than this threshold, I allow, for example, reinforcement learning to adapt and to make some mistakes. But if these mistakes leads to the situation where the quality of your service drops below this threshold, you should just switch to your already known algorithm to control the situation. So it's like that you are allowing experimentation when the situation is more or less good, and restricting your machine learning part, then it's critical for functioning of the system. And then with the classical, your traditional algorithm, you can drive it back to the more or less good state.
Should I give a comment? Then you can see.
Sorry. Yes, but if we need to create a hard algorithm, if we need to create a control system above narrow, where is the area for working with narrow networks if we have to control them? We need to provide a lot of work, so we can only create create hard decision and work without neural networks. This is a very complicated work. We have now a lot of time, we have deadlines. We can't create very complex system with control system and control system. This is chaos. I can't understand where is a good solution.
My idea was actually that it's like you need to use adaptive algorithm only to improve over the solution you already have, and but as it's algorithm which can be trained and which adapts to your system, you don't need to provide solution for this reinforcement learning algorithm. The only you need to feed is the quality you need to achieve. So you provide like rewards for good behavior or some measure of quality to adapt. So it's in terms of your effort, it's not very hard because you anyway you measure how your system performs.
Okay, second.
I will give a very general answer to your question. You know, when you start working through neural network, let us say control systems. Now, there are various parameters which are used as the control variables. So how do you know that? So for a neural network, let us say, ask the question, what should be the input to the neural network? So this is the first question you have to be answered. Now, the physical system which one has created, that cannot exactly be same copied on the neural network. Because neural network is a mechanism, is not a system. And that mechanism has to first find out. So in social science, these days people go for what is called as a qualitative analysis before going to quantitative analysis. In the qualitative analysis, what one has to do is take few either use cases or some done experiments. Not large numbers, but only 1, 2, 3, 4, 5 experiments. And then they try to find out what are the independent parameters which is controlling our whole experiment. So those control parameters which are orthogonal, that is very, very important. They has to be found out. And what the neural network does is that from the input layer, when it goes to hidden layer, at the hidden layer, our understanding is that each node represents one feature. And what is that feature? That is independent of each other. So in one layer, all the nodes, so in the hidden layer, if there are 5 nodes, it means 5 features are there, and it is forming one vector of 5 features. So finding out these feature vectors is important, and that has to be done through some analysis on the experiment. Finding out this is a critical part. Now, once someone has found out these 4 or 5 features which controls our experiment, then there are 2 things. In all neural networks, there is one which is called as the generalization. So how much general our deep learning network is. And to use that knowledge, you require particularization. So general knowledge cannot be used in all as in raw form. The general knowledge has to be tuned to the particular knowledge, to the particular system to use it. So these 2 things are required. In that case, how much we can tune? What is the variability of that is one of the very important factors. And that's why when I talked about type 2 fuzzy neural network, in this case, we find out the footprint of this one, that is one lower bound and one higher bound. Anything beyond that lower bound and higher bound, this algorithm will not be able to follow. So you have to find out a lower bound and a higher bound. So create 2 functions. One is the lower bound and another is higher bound. And that is the general form which can be used as through neural network as per generalization. For using that, do it on some data, real data in the system, and then tune that to particular
publications, but these publications are talking about the theoretical results. There is, as of now, there is no practical demonstration which has been done. Faithfully, results are available. There is no something like this, but it is having very, very robust foundation. So as far as the next generation air interface is concerned, this is my opinion that we have to look into 2-3 different aspects. One more aspect which should be there, which should be considered for the next layer interface is the modulation technique. So the OFDMA actually, which was there for the 4G and it has been carried to the 5G as well. Actually, this is something which requires reconsideration, and probably most of you might be aware of this thing, that that orthogonal time frequency space modulation technique, which was actually a group of new startup started working on this. A lot of experimental results they have obtained, and actually at the time of this 5G specification finalization, they wanted that this should be a part of the physical layer specifications of the 5G. Somehow it could not be available, and then they released this particular their findings to the academic world, and now a lot of people are doing. But if you just see it, it's a very, very innovative in a way that instead of the time frequency domain, the OTFS is dealing with the delay Doppler domain, and it is having a larger duration consistency. So this is something very, very important that we need to understand, and whatever I could understand over there, when we actually try to figure out all these things and combine all these things, then it appears to me that artificial intelligence definitely has to play a major role. What kind of, suppose we have some NT number of antennas at the transmitting and receiver end, but AI can tell that actually it is how many number of antennas are required to be used at a particular instant of time. You are not required to use all the antennas all the times. So these are the very, very crucial informations which should be made available by the artificial intelligence algorithms. What should be those algorithms? Definitely a lot of research is required to be done. So this is my input from for this discussion.
Thank you very much. If somebody else wants to say, please.
Thank you. I want to continue the topic about channel state information and have several notes. Maybe we can also discuss on this topic. Actually, one of them, for me, if we say about neural networks, it is something like implicit representation of real data and some kind of approximation of some physical laws, if we say about channel, propagation channel, which is well defined by Maxwell equations, and maybe some even simplification. From another side, when we want to use neural networks, it seems we try to, make some abstraction from mathematical formulation. Also, we want to ignore some physical meaning and just focus on this neural network structure and learning procedure. And do you think that such blind behavior for neural networks with limited data set will help us more than if we can introduce some data model-driven system and create a mathematical formulation to solve problem of equalization and demodulation? This is maybe one question. So it still will be more like simplification from performance of view if we use neural network. And another question maybe about real data. All you mentioned the importance of real data, but in 3GPP, in standardization, there is a lot of measurements of the channel and a lot of real data collected before the model was defined, channel model. So 3GPP channel model and all channel models, they are usually based on the real data. And channel model just also some type of representation of this data. And maybe channel model itself can be something like artificial generator for the data, and then training procedure can be based on the channel model sequences. And we just need neural network structure which will be more or less robust to such data and generate output for real environment, which almost keep structure in the model and in the physical environment, because channel model almost consider physical laws, and it is not random model like maybe first version of the channel models. This is questions about. Yes, and then I have one about source code.
I can give maybe my view as I'm not doing. I'm not familiar with specifically with telecommunication, but in general I can comment on this. It's like a general trade-off between model-based and like machine learning-based representation. Actually, if you have some process where you have good model and where you can have all the initial conditions to calculate your model, and if calculation is feasible, then your model is much better than any you don't need to spend time and resources for training like approximation of your model. On the other hand, if you you are not sure in your model that some variables may be not included in it, or then you cannot estimate all these initial conditions to estimate all the states produced by your model, then you can use machine learning. Or on the other hand, consider the problem of like protein folding, where you can have a full model and the full initial conditions, but calculating, optimizing this model to have a 3D structure is very computationally demanding. So you can use like machine learning, neural network, to train it on the data to have like approximation which is much faster than this your full model, and then it will allow you to save your computation time. So I think that you need to use these machine learning techniques in two cases. One case when you have some missing variables in your model or in initial conditions, or if computations for your model is very resource demanding. So that's
Can they complement each other? Maybe I still want to use my model, but I want maybe.
So actually, maybe you can do this if you if you have a good estimator which can say if your classical model performs good or not. So if you can measure, for example, your prediction error, and if it's like higher than some threshold, you can switch to, for example, to more computationally demanding neural net models, which can help you in this situation. Maybe.
Maybe then another question about neural network application when physical model still complicated. Then there seems one way. Okay, I'm agree with this. It can be machine learning based algorithm. Another way maybe to introduce low parametric models and to check how much robust and precise model can be from low parametric description of the physical phenomena. And can data-driven approach help us to extract low parametric model? Not replace, but maybe support to find such
I think that it's a good idea, and many people would be happy to find some way to distill low dimensional models from the neural networks. But what we have now in the field, it's like an opposite. That the bigger the model, the more parameters, the better it behaves. So it's
complex.
Yes, but still it's more robust and so on. So you add parameters and you expect that maybe worse behavior, but still it has better behavior. There is, I have no, I've seen no works for like general method to distill neural network to boot model. So it's, I think that it's open problem.
Thank you.
I will just add to that and what Professor was saying. You know, neural network is not one network. So it is a name to given a different types of network. And the structure of neural network has something to do with what problem you are solving. The only problem is there are no mapping equations based on which I can say this would be the structure. So neural network structure and the number of nodes at different layers is a very important point, number one. Number two, the learning or activation theorem and the bounds are very, very important. Generally, we do not analyze that. So, if you keep weight as a constant, so what you are assuming is that given a mathematical model, I can compute that in terms of some weights and inputs. And having three layers, so applying three functions one after another in iteration. This is an assumption. And therefore, there are different kinds of networks, neural networks, which has been tried for. Say, for example, we can have a time variant weight. Okay. We can have a parameter of optimization, which has also a loss function. And we can have negative weights. Or we can have, like in brain, you have two types of neurons. One is called excitatory, another is called inhibitory. So what happens that if there is a particular pathway, so there is another pathway, and there are some modulatory neurons. So some of the modulatory neurons can give some input which will prohibit one pathway and create another pathway. So similar kind of structures have been created in neural networks where the neuron itself works as an inhibitory. So some of the inputs will not go up to the output in particular cases. In some other cases it will go. This is one structure. Other structure is people have created a decision network where each node is neural network. So you are combining both things. A decision network is basically rule based, and then each node is a neural network which computes something. So this kind of hybrid networks have been created and they are very successful. There are some other experiments which talks about complex weights. So you take a dual property, dual quantity, one is a dual of the other, and create the weights and energy and other things in those terms. Then the quantity you maximize or minimize. Some people are using entropy. Rather, the new trend is not energy-based parameters, but entropy-based parameters, and that also relative entropy or mutual entropy, and which changes with time. So there are many such, so one should not think of neural network as some constant thing which has to be taken like this. The kind of model you have and the kind of neural network you create has to match in some way to give more and more accurate results.
Do you think that entropy of the neural network can define how many use cases it can cover? Much?
Not in those terms, but at least entropy gives you, because information can be measured only in entropy, not energy based. Energy does not give any information there. Rather, energy can work as a constant. So, therefore, the new things will define parameters, errors in terms of there is an entropy gain or not. If there is no entropy gain, then why to learn more? So the convergence criteria is no entropy gain. Whereas without having some standard data, you can have a method of learning.
Because that is an important point in telecommunication system.
Yes.
We have information entropy, and structural entropy, and they should match each other, like channel capacity and rate capacity. And
I think that can be used, I don't know.
I can add some comments to this discussion. First of all, we have a huge field of mass where power of neural networks is exploring. For example, when we're talking about classification, we have such called CV dimension, as I remember. This strong mass describes what is the power of classification of neural networks, describing of amount of neurons, describing amount of layers, and some others. No? Okay. So we can try to explore our neural network, and starting with your question. I think we can see on two cases. First of all, we can include our physical model or some mass equations in our neural network. So in this way, our network can't work in opposite way with our knowledge, in our physical knowledge of process. And in the other way, we can explore our physical model. For example, we can work in L1 and L2 metrics and drop some parameters of our research. For example, we have a lot of parameters. We try to train our algorithm, our network, our machine learning, and after that we can see what of these parameters have huge weights or low weights. And in metric of L1 we have 0 weights from some parameters. After that we can destroy them and see on our physical model what is the combining of these two explorers.
I don't think that like your input parameters would be that independent. So it's usually to make models simpler, you need to make some additional like assumptions how your parameters are tied together, and then embed this dependence between parameters. So I don't think that it would be that easy to find what is not necessary in the case.
Can I? Yes, of course. This is true. In usual case, we have combinations of parameters, but when we describe our real system, we can use some methodology. For example, if we drop one of the parameters, we can decrease our metric, our quality, for example, on 2, 3, 5%. And in this way, it can be very good solution, because collecting data, for example, the real system also in networks where we, for example, working with users and collecting their ages, photos, and after something like that. When we drop some of them, we also can have good quality of our system. And when we are describing some physical layer of network, or if they am on something like that, we also can have a good result, but not the best result. I don't. I would not say that we must write the equation of physical world. What is yes, that's it.
Anybody else has comment, please? Professor Chenny.
This is a very interesting topic. I was wondering, since 5G will be deployed soon, while 6G is under the horizon.
Please come here. I will
okay.
be able to see you.
Okay.
Face communication is more.
It doesn't matter. Yeah, see me. That's just the question. So I was wondering, because 5G will be deployed soon, while 6G is under the horizon. So I was wondering, for 6G design, because right now when we talk about how to utilize AI to maximize the utilization of the existing network, right? So basically the network is there. So we're trying to utilize AI to improve the efficiency or maximize the utilization. While for 6G, is that possible when we start our design, we use AI to, the other way around. Basically I was thinking, is that possible? This is one question. Second question is, myself is also the mobile service user, right, customer. So sometimes even myself, I don't truly understand my need. So is that possible to use AI to actually understand the individual person need, not on the statistic basis. So from that perspective, is that possible to use this method to train the customer instead of just from the supply end to satisfy all the demand from the customer? So this is my guess. Okay, thank you.
So as I can understand, are you talking about the feasibility of 6G systems, or? Yeah, I mean, my view is that 6G is an extension of, think about a situation when smart homes, starting from IoT, so smart systems, you go to smart homes and smart cities, intelligent transport systems, 3D transport systems, that is going to be reality very soon. So you have, sky channels, air taxis, and where you have to create traffic rules for the sky. So that will be really very, very complicated. Then you think about smart cities, where the traffic control should not be related to each crossing only, but the whole city as a whole. Similarly, you start thinking about such applications together, where voice, video, etc. becomes a very small part of the whole utilization. Think about GPRS data, think about maps available to everybody, think about IPTV in every device, think about many such cases, and I think the TV programming will go. So what will happen is that you can have asynchronous kind of, whichever program you want to see, you can see. And the whole world will have a paid channel, so you can choose from any of the channels of the world. And these are going to be very reality very soon. So think about that situation. In such cases, I think the 5G will not have capacity to handle. Only in such cases 6G will be there, and I will say there is no other way out.
So you're going to spoil the customers. So whenever they require any information or service, it will be immediately available.
Yes. I think that you are absolutely correct in saying that since now we are having an opportunity, 5G is just about to be deployed, And now it is clear that artificial intelligence is actually a major player. So in the 6G when we are planning, definitely from before actually planning anything, the AI should also take part in the planning process. And this is absolutely right. So AI should be involved in the planning process, and definitely there are 2-3 things actually which are missing in the 5G, and this is something which is integrating with what you are looking at. So if we see that 6G when we are going, we have to go for the higher frequency, and it means that the network will converge. And as of now, whatever two-way relaying concept is there, or the cognitive network concept is there, specifically I am very optimistic towards the underlay and overlay cognitive network techniques. But if you just see the way this has been introduced in the 5G specifications, these are just there for the fancy, these are the fancy items there. But if we properly actually use AI at the initial stage, then definitely we can see that at the first place, should we have a connection establishment under which particular mode. Actually, this is also very, very important. Cognitive network technology is really having a great potential. But if we see the kind of developments which have been taken place whenever we are talking over, whenever we are making any standards, actually we could not find the way this should be integrated into the system specifications itself. So it took actually a lot of time actually for integrating MIMO itself into the core area of the specifications part. I guess that in the 6th generation system, all this will be integrated in a more systematic way, and we will have a much better system.
Thank you.
Thank you very much. I think that we need to finish our discussion. All people is rather tired. I can make set some joke that Professor Song shows me one maybe more useful way. Now we are training neural networks, and soon neural networks will train us, and maybe maximization of performance of communication system may be easier achieved by training users. Thank you very much.